Good afternoon again. Let's continue our chapter 27, problem solving. I have three problems here for you. The first one is number 21, and the topic here is slit diffraction. So gratings and what happened when the light passed through a grating. There has a certain number of lines, certain number of slits per unit length, and in this case, for number 21, the question is, a diffraction grating has 2,000 lines per centimeter, which means that I have 1 centimeter where I have 2,000 slits on it. Okay? At what angle will the first order for a maximum will be if I shine through this grating a ray of light of single wavelength to 520 nanometers. So the grating is 2,000 lines per centimeter. We want the first order, so m equal 1, and the lambda, the wavelength of the ray of light, is 520 nanometers. Okay, so the first things we want to do is find how far apart are two slits together. I know that each centimeter is divided in 2,000 slits. So in order to find how many slits you have, or sorry, how far apart two slits are, you just invert that number. So the distance between two slits is essentially 1 centimeter, which you know has been divided in 2,000 times. And so each slit separates from the other of 5 times 10 to the minus 4 meters. The question asks you, what is the angle of the first order? Well, this is the equation, d sine theta equal m lambda, where m is equal to 1. And so the angle of the first order is the sine to minus 1 of m lambda over d. Plug in the numbers that you have, and you get 5.97 degrees. Okay. The second problem is number 26. I know there is a little bit of glare here, but I'm going to read the problems, and you'll find that it's sort of similar to this one. So an electric current through a hydrogen gas produces several distinct wavelengths of visible light. What are the wavelengths of the hydrogen spectrum if they form first order maximum at the following angle: 24.2, 25.7, 29.1, 41.0, when projected on a diffraction grating that has 10,000 lines per centimeter? So what is the idea here? If you take a hydrogen gas, you heat it up, this hydrogen gas will emit light. And it turns out that the light that emits is not monochromatic. It's not just one wavelength. It does have specific wavelength. And so when you pass through a diffraction grating, of course, because depending on what lambda is, theta changes, okay, they will produce wavelength of different color, okay? Sorry, rays of different wavelength which correspond to different colors. So the first things we want to do is figure out what the distance is between the two slits of this 10,000 per centimeter grating is. Okay, GR is my way to say number of lines or gratings. Okay, so you can choose the way you want it. But similar to what we did earlier here, if I want to find what the distance is between two slits, I just invert that number over there. So it's 1 centimeter is being divided by 10,000 slits. So the distance between each slit is 10 to the minus 6 meters. Okay. Now the question is, what is the wavelength of each of these component once we know the angles? Well, the angle that I labeled here is theta subscript A, which is the first angle, which was 24.2 degrees, corresponds to a wavelength, lambda sub A, equal to d, the sine of theta A. There should be an m underneath this, but I already know that I want the first order. And so I just omit that one, which is m equal 1, okay? So you plug in the number, you get 410 nanometers. The second angle, theta B, happens to be at 25.7 degrees. And I know here's the glare. I'm trying to You see just like a symbol there. So the lambda b is d, the sine of theta b, divided by m equal 1 again, because I want the maximum. And that happened at 434 nanometers. And then you can do for all the others in the same way. Okay? So that's why I didn't write it down the others. The third problem I have for you for this video is number 28, and I have it on the right board. And the question is, what is the maximum number of lines per centimeter that a diffraction gradient can have and produce a complete first order spectrum for visible light? So visible light, when it goes through a grating, splits. And so you have the violet or the shortest wavelength having the smallest angle, and then the red wavelengths having the maximum angle. Okay? So the question here is, what is the maximum number of lines so that when you project it on the screen, the red is still visible? Okay? So we did this in a different way in class, but here's the idea. This is the first order, so m is equal to 1. So d sine theta is equal to lambda. Therefore, the distance between the slits is lambda over sine theta. In order to be able to have these red wavelength inside the screen, theta has to be less than 90. So the maximum value that you can have is sine theta 1, sine theta equal to 1, which means theta is equal to 90 degrees. And so if you plug in this 90 degrees in this equation, you get the maximum distance between the two slits has to be lambda. And for red wavelength is 780 nanometers. Okay? Now I have the distance between the two slits, and I want to make a grading of that type. How many times I can split 1 centimeter each of two slits being at 780 nanometer apart? It's the opposite problem that we had here, where we have the size of the slit, sorry, the size of the gratings, 2,000 lines per centimeter or 10,000 lines per centimeter, and I want to calculate the distance. Here I have the distance, and I want to find how many slits I have, which I call n. So now I just have to use this formula and invert it. So n, the number of slits we have, is 1 centimeter, which I wrote as 10 to the minus 2 meters, divided by 780 nanometers. Again, you have to play with the units a little bit. The result is 12,821 lines.